on a Stone Age island at the ends of the Earth is an astonishing superstructure whose very existence defies imagination. To build it, men climbed mountains no one could climb, gave their lives building roads no one could build, dragged the world's biggest trucks and shovels where they could not go, thousands of feet into the sky, into a deadly realm of blinding fogs and perilous quests for staggering riches. They did it all to mine a hidden fortune, a mountain made of gold. In our age of satellites, cell phones, and cyberspace, there are still a few hidden places left on Earth. One of them is Irian Jaya. A land born of fire, crowned by ice, where pathless jungles swelter in equatorial heat, where freezing mists envelop soaring mountains, and men still live untouched by time. Some 75 miles from its jungle shores, a wall of mountains soars to 16,000 feet, the highest peaks between the Andes and the Himalayas. Atop them gleams a natural wonder, magnificent glaciers spawned by the Ice Age some 15,000 years ago, only 5 degrees south of the equator. Just below these glaciers lies a wonder of man. 2 gigantic mines called Grasberg and Erzberg, less than 2 miles apart and nearly 14,000 feet high. Before it's exhausted, this megamine may yield more gold than the entire California gold rush. Many call it the most spectacular mineral deposit ever found.
It's a mountain of ore, but it's not just that, it's also a root of ore. So like if you had a tooth, you know, and you can see the part that sticks above the gum, that's what most people mine. But if you extracted that tooth and it's got that long root on it, we've got that as well, and it's also full of ore. So you're looking at a vertical mile of gold ore body. It's just incredible.
Grasberg and Erzberg lie some 700 miles north of Australia and 2,000 miles east of Indonesia's capital, Jakarta, in the western half of New Guinea, second largest island in the world. Once a Dutch colony, Irian Jaya is now an Indonesian province and home of some of the world's richest deposits of copper and gold. But Irian Jaya is not surrendering its treasures without a fight. The Grasberg-Erzberg mining complex took 20 years to build, cost more than $3 billion, and took its toll in human life. At its dizzying altitudes, men must work 24 hours a day, 7 days a week, to make mining profitable in one of the most remote locations on Earth.
The tough part about this is that Mother Nature implanted this wonderful ore body at 13,000 feet. And she said, come get it. And we had to go get it.
When you go up there to try to explain it to somebody, the best way is that you're going to walk away with your mouth open. You're going to be agog. people are going to say, how in the world did you do that?
This incredible story begins with one man, a Dutch geologist named Jean-Jacques Dozy. In 1993, aged 84, he returned to visit the mine his courage made possible. In 1936, 27-year-old Dozy vowed to be the first man to reach Irian Jaya's tropical glaciers. It seemed a reckless boast. Europeans had been launching expeditions to Irian Jaya's hinterland for 300 years. None had broken through the deadly labyrinth of jungle between the mountains and the sea.
The only way to make your way inland is by river. Now, the problem with the rivers is that you don't know where the rivers are leading. This was a problem with the very first expeditions that came to this area that tried to reach the glaciers that took the wrong river. They spent a year and a half trying to get to the glacier just because they took the wrong river.
It seemed unlikely that Dozy would succeed where so many others had failed. But Dozy possessed a recent 20th century invention, which lifted him over the jungle and showed him the way to go.
Dozy had the advantage of knowing what the terrain looked like from the air. Once you knew the terrain, once you knew which river to take, once you knew what the lay of the land fairly well, you could move a lot faster.
On October 29, 1936, Dozy, 2 friends, and 8 porters started up the Ikwa River. They paddled to where the mountains began and started walking.
We just walked up as far as we could, started cutting, followed a trail, made a trail, and the higher we came, the more tougher it became.
After a while, they didn't know where they were anymore because they had aerial photographs up to a point, but then the jungle gets pretty steep and you're not quite sure how far you have to go.
Exhausted as he was, the geologist Dozy took time to sketch a peculiar rock formation.
You had a black rock wall, a black mountain with green and blue large specks on it. And well, being a geologist, I of course recognized that there should be some copper into that rock, but at that moment I had to go on.
Dozy had no way of knowing how right he was. In fact, he had stumbled upon one of the greatest geological discoveries of all time. Three million years ago, a series of volcanic eruptions injected riches into the mountains of Irian Jaya. The erupting volcanoes opened up cracks deep within the earth. Propelled by hot gases, molten magma from the Earth's core flowed into these fissures, carrying with it unusually high concentrations of copper and gold. One of them was Jean-Jacques Dozy's strange black mountain, the biggest copper deposit ever discovered above the surface of the Earth. Dozy collected a few ore samples from the curious copper mountain. On his field maps, he named it Grasberg, Dutch for Mountain of Ore. Back in Holland, he wrote a report describing his discovery. But his timing could not have been worse. Dozy published his report in the summer of 1939. On September 3rd, World War II began. While Holland suffered under Nazi occupation, the Grasberg report gathered dust. 20 years later, a Dutch geologist gave it to Forbes Wilson. Wilson was chief mining engineer for Freeport, an American mining company.
Forbes was a man who had to be the best or the biggest or the fastest or the smartest with anything and everything. And indeed he was in many areas. That's part of the reason I think that we today are mining in the Erzberg complex.
Wilson was looking for nickel deposits, but when he read Dozy's description of the Erzberg, he forgot all about nickel.
After Forbes Wilson read the Dozy report and it became part of his being, we can almost say that it became a holy grail for him. He was a man 50 years old at the time and a heavy smoker. He gave up smoking, got himself in shape, and organized this expedition. He had to find and see for himself Erzberg.
On May 30th, 1960, Forbes Wilson plunged into the jungle, determined to reach the Erzberg. He asked his friend and fellow geologist Delos Flint to come along. Flint jumped at the chance to take part in the adventure of a lifetime, despite the perils of trekking through Irian Jaya.
The worst thing there were the leeches. And if you looked at a bush, the leech would be there trying to find something warm that he could attach to. We'd always get a few. And one time I found one on the roof of my mouth. If I hadn't been busy talking, I guess I wouldn't have had it happen.
But leeches weren't the only unfriendly locals. Only 1 year after the Forbes Wilson expedition, the explorer Michael Rockefeller vanished in Irian Jaya. Some believe the son of Governor Nelson Rockefeller drowned or was killed by sharks, but others are convinced he was eaten by cannibals. When Del Flint and Forbes Wilson first encountered Irian's indigenous peoples, they felt threatened, but for a different reason.
Even though you've seen pictures of them with their gourds covering their privates, the first time you see it, it's a real shock. You feel very, well, unequipped, that's the way I would put it. They came in with all their finery and charged like they were being arrayed in war, which sort of gave you, you know, but they turned it into a dance and everybody was happy.
On June 16th, 1960, after 18 days of hard travel, Del Flint and Forbes Wilson found the Erzberg. A surface inspection convinced them that it was indeed a mineralogical marvel, thickly laced with enormous chunks of the yellow copper ore known as chalcopyrite.
There'd be blobs that up to 4 feet across, or perhaps even longer, that were solid chalcopyrite. And when you saw that, it was just, you boggled your mind. When I first got there and got up on the thing, I just screamed like Tarzan, "Yoo-hoo, God, it's mine, all mine!"
The two American geologists had proved that Erzberg was really a mountain of ore. But Jean-Jacques Dozy had called it a mountain of ore on the moon. Who could build a mine in one of the most inaccessible places on Earth? In the 1960s, Irian Jaya's mountain of copper and gold appeared as spectacular as Forbes Wilson believed it would be. Rock samples from Erzberg had one of the highest copper contents ever found. Yet no matter how rich it was, Erzberg was virtually impossible to reach. But on April 5th, 1967, with authorization from the Indonesian government, Freeport decided to try. To build its mine, Freeport hired Bechtel, a California engineering firm with a reputation for building things in places no one else could. But even Bechtel's engineers were stunned by Irian Jaya. To even reach Erzberg, engineers would have to build a 75-mile road through some of the toughest terrain on Earth. First, through the labyrinth of mangrove swamps hugging the coast. Then through the seemingly impenetrable jungles of the lowlands. And finally, over mountains that rose like walls up to 16,000 feet high. They had no airport, no seaport, and no place for helicopters to land.
Well, the first thing was to build a dock area and to put in a road. Well, both the dock area in the mangroves and the beginning of the road, you had to drop everything down from helicopters. You had to drop people down from helicopters to saw off trees to make platforms where the choppers could land to bring in supplies. They would get their people into choppers, put them in a hoist with a chainsaw. The people would come down from the chopper with their chainsaw going. Now, remember, they're dropping down on a solid canvas of treetops. So they would have to cut their way down to the floor of the jungle as the helicopter tries to hover, and the master who's inside the helicopter is watching to make sure that this guy doesn't start bouncing around back and forth. You can be slammed against a tree. People have been killed this way.
As crews cleared helicopter landing sites, road building began. Workers came from all over the world to take on the incredible challenge. Among them was a young Indonesian from Sumatra named Ilyas Hamid.
When I was selected to come here, I was a little bit afraid because I heard there were almost no people in this place, and also some rumors that people in this area ate other human beings. However, when I shared my concern with my family, they gave me their support and told me to leave my fate to God.
Engineers dredged tons of gravel from riverbeds, trying to create the foundation of a road. In the worst places, it took as much as 50 cubic yards of gravel to build 1 foot of road. Overnight, while the road builders slept, the road they had built the day before often sank into the swamp. In places, Bechtel built 2 miles of road for every mile that survived.
Working in this place was very difficult. I thought that after digging mud for 3 to 6 feet, I would get to hard soil. But in fact, we were still finding mud after we had dug more than 30 feet. In one day, we could make only 15 to 20 feet of road.
As the road inched forward, landslides buried tractors. Trucks fell into rivers. Helicopters sank into swamps. And that was the easy part. 50 miles from the coast, the sheer wall of Irian's backbone rose up as steep as 70 degrees. The mountaintops were razor-sharp ridges, in places only 2 feet wide, with vertical drops on either side. Yet 25 miles of road had to be built over those mountains if Erzberg was to be reached.
If you're willing to put enough S-curves into the road, you can put a road up almost any slope. Then the problem is to put the road along the ridgecrest. Now what Bechtel did is from helicopters, they dropped down very small bulldozers that are the size of small lawnmowers. They would drop these down, and these bulldozers would cut off the top part of the ridgeback. And then slightly larger bulldozers would come in. Bechtel went through 6 size bulldozers between these very small lawnmower-type bulldozers until they got to the big boys the size of a house, which eventually did build the road. So you started getting a flat ridge line, and then you started going down in S-curves, going down to the bottom. Tremendously difficult. Bulldozers would fall over the edge. Who knows where they ended up?
The bulldozers pushed forward. Drivers kept one eye on the dizzying drops below them, and the other on the crumbling cliffs above. No one knew if he would live or die.
One day, my bulldozer broke down, and the helicopter could not bring a spare part. The next morning, my friend, an American whose bulldozer was working, replaced me as the leader of the work. After only half an hour, the land he was working on collapsed, and his bulldozer slid down into a canyon. As he fell, a tree branch speared him right through the chest and killed him.
By 1971, after nearly 4 years, victory seemed in sight. But 7 miles short of Erzberg, the road builders ran into a towering 2,000-foot cliff. Bechtel's engineers had an ingenious solution. A helicopter carried a 9,000-foot-long nylon rope to a platform at the future mine. With this bolted in place, workers hoisted up ever thicker ropes until the line was strong enough to hold steel cables as thick as a man's arm. This web of steel became the longest aerial tramway of its day and one of the steepest. Its cars rose 2,000 feet in less than a mile. But no one anticipated the mysterious vibrations that shook its cables.
Vibrations would be so strong they had to stop everything because the ore cars would vibrate right off the cable. They called in a Swiss mathematician. He said these cables are like the strings on a very fine violin. If they're a bit out of tune, the violin sounds lousy. He recalculated speeds and stresses. Since then, everything has gone very smooth.
With the tram in place, Freeport could lift men and equipment all the way to the mine entrance. At the tramway's base, Bechtel built mine offices and an ore processing mill. After 5 years of battling Irian Jaya, the Grasberg Mine was ready for operation at a cost of over $1 billion. But engineers had to solve another problem. How were they going to get thousands of tons of ore down the mountain? By 1972, engineers had met the challenge of building a road through Irian Jaya. Miners could begin digging the huge deposits of copper and gold discovered there. Soon, they were mining thousands of tons of ore per day. But they also faced a new challenge: how to ship that ore from Irian Jaya's faraway mountains to the rest of the world. Trucks and trams couldn't carry enough ore per day to make Grasberg profitable. Engineers came up with a simple solution to moving the ore. Let it fall. Newly mined ore begins its journey to the world through a series of ore passes. These giant chutes send it plummeting 2,000 feet to the base of the tram. As the ore hits the ground, it breaks into smaller pieces, making it easier to move. Conveyor belts rush the fallen ore to a mill. Inside the mill, it pours into the world's largest ore crushers, some nearly 40 feet in diameter. Whirling inside these enormous drums, thousands of steel balls attack the ore, grinding it into smaller rocks, and finally into a powder. At the mill, workers mix powdered ore with water to create a concentrated liquid slurry of copper and gold. But this concentrate is still 10,000 feet high and 70 miles from the sea. Gravity gets it there. Mill workers pump the concentrate into a pipeline running beside the road. After 20 miles, the descent becomes so steep that gravity alone carries the concentrate another 50 miles to the sea. Piled in barns by the ocean, awaiting shipment to smelters around the world. The product of hundreds of millions of dollars and years of hazardous work looks like nothing but a huge pile of dirt. But in fact, it's pay dirt. When it's smelted, each ton yields nearly 700 pounds of copper, 30 grams of gold, and another 30 grams of silver.
We mine the ore at 14,000 feet and we sell it at sea level. And that's a 75-mile distance between those two. Nobody else does that.
In December 1972, the first ship loaded with ore from the Grasberg Mine sailed from Irian Jaya. By the 1980s, Grasberg was a huge open-pit mine. The ancient glacial meadow sketched by Jean-Jacques Dozy echoed with the sounds of one of the world's most ambitious mining operations. But Freeport knew that big as it was, Grasberg wouldn't last forever. The company sent geologists deep into the surrounding mountains to search for an even bigger body of ore, a mother lode that would make mining in Irian Jaya profitable long after Grasberg had played out. It was a dirty, dangerous, thrilling job for a few exceptional men and one exceptional woman.
We spent many times really running for the helicopter. You'd be just exhausted and you'd just get in and almost collapse, but it was either that or spend the night, and it was very cold up there at night.
In the early 1970s, Frank Nelson was one of the first geologists to explore the wilds of Irian Jaya. Working with him was his wife Eleanor, also a geologist.
Our first chore really was developing a map, first topographic and at the same time geologic.
We had one camera that we mounted below the helicopter that Frank would work on a remote control, and I took handheld pictures out the door of the helicopter. Just open the door and point the camera out.
And sort of surprise our drillers sometimes. They'd say, who in hell is that up there? And Ellie'd be sitting there at the edge of the seat with her feet off the edge and shooting straight down and trying to get a montage, a mosaic of the area. And even these big, rough, tough Maori drillers, they were impressed by that. So that is one cool woman. People were not familiar with the natives, and we were lucky enough to have more direct day-by-day contact with them. And you got to really like them. A lot of people feared them. They looked pretty dramatic, I mean, with painted faces and, you know, bones in the nose and bows and arrows, and they were, you know, ominous looking. But actually, when you got to know them, they had a great sense of humor. We used to ask them for the fun of it, and they always would say, well, not us, but over in the other canyon, those fellas, yeah, they makan orang, you know, they eat people. And they go over there and say, oh, not us, but those fellas had.
By the 1980s, the Grasberg open pit mine was no longer profitable and was shut down. But by then, Frank and Eleanor Nelson and other geologists had discovered huge underground copper deposits nearby. It was a rich find, but it wasn't the mother lode Freeport had been searching for. In fact, in the mid-1980s, Freeport almost quit mining in Irian Jaya as a new technology threatened to destroy the world demand for copper. Fiber optic cable was revolutionizing world telephone systems. Many believed it would soon make copper telephone wire obsolete. But in 1984, a new chief executive took over at Freeport. James Robert Moffat was a field geologist who'd spent years exploring for oil and minerals. He wasn't ready to give up on Irian Jaya. He believed in the mother lode.
I looked at New Guinea and saw Papua New Guinea with hundreds of mines that had been explored over the last 150 years, and Irian Jaya with basically the small Grasberg Mine. And it's what we call state line geology. It happens all the time. Just because this terrain was so horrible in terms of trying to explore it, and people quit at the Papua New Guinea border, and they began to tell themselves that this state line really was some sort of a geologic boundary. Well, that's ridiculous. Geology doesn't know political boundaries, and it never has and it never will.
Moffat was convinced there was more gold in Irian Jaya's primeval hills. He told his geologists to find it. As it happened, a Freeport geologist in Irian Jaya had been thinking about gold and staring at a mountain called Grasberg, less than 2 miles from the Grasberg Mine.
Every morning I'd look up and I'd see the outcrop, I'd see that mountain sitting up there, and I'd think to myself, gee, there really should be something up there. It literally drove me nuts to stand down at the bottom of that mountain and look up at it and know that there was a rock up there that I hadn't been on. And that was an itch that I just had to scratch. And after about 2 years, we finally got a chance to do it.
The rocks Dave Potter collected on Grasberg assayed at 1 to 2 grams of gold per ton. It was enough to justify further investigation. Potter set up diamond drills and took core samples.
The first one came back, which was an angle hole that went directly under the outcrop, and not only did it have gold in it, it also had copper values. And for the first time, I started thinking to myself, there's something more here than just a gold deposit. The one that really drove it home was the last hole that we drilled. It went over about 1,500 feet deep. And out of that 1,500 feet, all of it but about 90 to 100 feet came back with copper values that were ore grade. In other words, they were on the order of 1 to 2% copper, on the order of 1 to as high as 5 grams per ton gold. That hole was when I suddenly felt, my God, this is big.
Big was an understatement. Grasberg made mining history. Dave Potter's hunch led Freeport to 1 billion tons of ore, the biggest gold deposit and the 3rd biggest copper deposit ever found.
Give Mr. Moffat the credit for maintaining the property when he could have taken probably $75 million for it in the early 80s and walked away clean. You know, now Grasberg itself in the ground is worth over $40 billion. 75 million, 40 billion, good choice.
But as the first euphoria faded, a sobering realization took over. A wall of cliffs blocked the Grasberg road from reaching the Grasberg. To mine its bonanza, Freeport would have to haul the world's biggest trucks and shovels up Irian Jaya's nearly vertical cliffs to a mountain even more remote than Grasberg. At Grasberg, engineers had achieved the incredibly difficult. Now, at Grasberg, they faced the impossible. Grasberg is the world's richest gold mine. It's also one of the most productive and cost-efficient. Working 24 hours a day, 7 days a week, its miners dig 600,000 tons of ore in a single day. To dig this staggering amount of ore, they must use the world's biggest mining equipment. Gigantic Bucyrus electric shovels, picking up 80 tons of ore in a single scoop. And the Komatsu 930, the leviathan of ore trucks, carrying over 300 tons in a single load. Other mines use this colossal equipment, but none has faced the task of transporting it up sheer cliffs in a remote and primitive land to a mountain peak nearly 14,000 feet high. In the 1980s, this seemed impossible. The Grasberg tramway can carry only 15 tons. A single Komatsu ore truck weighs over 200 tons. Towering cliffs blocked the Grasberg road from reaching the Grasberg site. In the late 1980s, the Grasberg miners faced this daunting challenge and won. This is the heat road. HEAT stands for Heavy Equipment Access Trail. The heat road is unlike any other highway ever built.
The heat road begins at an elevation of about 8,000 feet and traverses up the mountainside for about 7 miles and comes out at about 13,500 feet. Some of the grades are in excess of 22 to 30%.
Branching off from the main road just below the Grasberg, the heat road zigzags straight uphill into the clouds until it reaches the mine, Freeport's stairway to heaven.
The largest single contributing factor to this mine is the heat road. If we didn't have the heat road, Grasberg Mine would not today be moving 600,000 tons a day.
Over this nightmare of a road, colossal trucks and shovels must be brought up piece by piece, like this ore truck chassis weighing 40 tons. In places, the road seems to defy the laws of physics, as its grades approach the maximum angle a fully loaded vehicle can climb.
The heat road shouldn't exist. If you look at the heat from down below, you don't even know what it is. When I bring people up for their first visit, they look and they just say, "What is that? What's going on up there?"
Many said this crucial road could not be built, or if it could, its cost would be astronomical. They hadn't counted on Freeport's veteran road builder, Ilyas Hamid.
Freeport asked several independent contractors from Australia to give them an estimate as to what it would cost to build a road. And the estimates came in dozens and dozens of millions of dollars. He heard about these incredible estimates and he thought to himself, this is crazy. I can do this for a lot less money than what these people are asking. So his expat supervisor agreed to let him try.
First, my boss took me to see the situation from the helicopter. I told him I needed a bulldozer, mechanics, and fuel. My boss said, "Okay, Ilyas, I give you everything you need."
So the guy just drove his bulldozer from the top to the bottom. It took him a while. He didn't do it overnight, but he just zigzagged back and forth.
It was the hardest work I have ever done. The bulldozer was always in danger of falling because the ground was very slippery and had very little soil on top. So the challenge was very big.
When you drive a bulldozer on a slope as steep as the slope going up to Grasberg, you can go over any time. He almost did several times. His nerve endings are so much better than ours in sensing that fine line between toppling over in your bulldozer and dying and being able to make that cut on which other people can follow behind you. That road was built for under $2 million. Incredible, just because of one guy who had whatever it took, brave enough, to go and drive his bulldozer from the top to the bottom.
He's kind of a mellow guy, but inside I think he's a tiger, and he loves the challenge. And he made something amazing happen. He maybe doesn't know much about the world of physics. Maybe he just says, "You want a road from A to B and I'll get you there."
The heat road conquered Irian Jaya's mountains. But steepness is not the only obstacle to be overcome. At nearly 14,000 feet, operating one of the world's biggest mines is a daily, dangerous challenge. Most mornings begin in brilliant sunshine, but by midday, clouds sweep in from the sea. Within seconds, visibility at Grasberg can drop from nearly perfect to nearly zero. Most days, the Grasberg miners must operate their Leviathan machinery in fog so dense they can barely see. The 200-ton Komatsu ore trucks, with their tires as tall as a house, could squash a smaller vehicle flat without stopping.
Now they've got very strict rules about what to do once the fog comes in, having your lights on, being X number of meters away from any other truck, who has priority, and these safety measures are followed extremely closely, otherwise people would be dying all over the place.
Ore truck drivers like Alexander Kromsian have been trained to handle dangerous weather.
If the fog is closer than 50 feet, I park my truck and wait until it disappears. I'm never frightened, although I worry a bit because the road is very narrow and slippery.
Like many Grasberg employees, Alexander Kromsian is an indigenous Irianese. His truck driving skills are even more impressive than they seem.
I had never operated a vehicle before. The company tested me when I came. On the first day of training, I was a little confused, but I did not find it difficult after that.
20% of my people are local Irian people who have never seen a Toyota before or a car, and they come up and they're driving 300-ton haul trucks. That's a challenge in itself. And we're pretty proud of our workforce, and I've worked at numerous mines, and I'd put my people up against any other mines in the world.
Grasberg's miners won't be stopping work anytime soon. Geologists believe the deposit is even bigger than originally estimated and may still contain billions of tons of ore. But Freeport has not given up its quest for new bonanzas of copper and gold. The search has sent geologists on death-defying explorations. Today, the Grasberg Mine remains the biggest gold deposit ever found. Freeport geologists continue their search for an even bigger one. Today's scientists have tools unimagined by the explorers of the past. They pore over magnetic imagery and high-resolution satellite photography, zeroing in on potential ore bodies they call hotspots without leaving the comfort and safety of their lab. But someone's got to evaluate those hotspots, and the only way to do that is the old-fashioned way. Jay Pennington's morning commute is a little different from most.
We just pop out of the helicopter basically 2 at a time with a sampling pack and a survival pack. And then we're 1 at a time down the hoist, say from 100, 120 feet, so like a 12-story building. The first time I was lowered out of a helicopter, it was extremely invigorating, and it was scary, and it was fun all at the same time. You got to have ultimate faith in your pilot, the hoist master, who's going to have your life on the line there for about 90 seconds, and then the people that maintain the equipment, both the hoist and the helicopter. So you get through that, and let's face it, you can't do the work without that confidence. As soon as you have that, the rest of it can be as fun as you want.
Exploration geologists like Jay Pennington are the front line of Freeport's search for the next Grasberg.
That's good stuff.
Despite all the high-tech science that leads him to a hotspot, Jay works with tools any California 49er would recognize. 8 hours a day, he pans for gold like an Old West prospector in some of the last true wilderness on Earth.
A lot of the times when you hit the ground, you got to feel that no Westerner, no non-native has ever been where you are at that moment right there. So you have the potential to stumble over a 50-ounce nugget of gold, and just as easily as you can step on a rare poisonous snake.
When Jay finishes sampling one hotspot, he radios for the helicopter to pick him up and take him to another one. But when a helicopter leaves Jay in the jungle, there's no guarantee it can return.
You can't fly if you can't see. You don't play mountain tag with a helicopter. It's not advisable. There have been times when you wind up in a sandwich of clouds. Okay, either one can get you from the top down or from the bottom up. And if you get a helicopter stuck in that sandwich, you're asking for real trouble. And then I'm there for the night, and that's happened a lot. When you're stuck out there, it's miserable.
Beyond all the adventure lies the ultimate dream, an ore body even bigger than Grasberg. In 1994, a Canadian exploration company claimed to have found it. Bre-X announced it had unearthed an enormous gold deposit on the neighboring island of Borneo. How enormous? 200 million ounces of gold, worth $70 billion. As Bre-X stock skyrocketed, the Indonesian government asked Freeport to develop the Borneo Bonanza. But when Freeport's geologists finally got a chance to test Bre-X ore samples, they made a shocking discovery.
What they were finding was particles of gold in that rock powder that were 10, 20, 50 times the size of the rest of the powder. So they were obviously salted.
The gold that we found in our samples that we had drilled and processed, the few grains of gold we did find were very small, minuscule compared to what they found, and it just told us that somebody had falsified the information by adding gold to the samples.
The Bre-X gold strike was a hoax. Freeport executives asked Michael de Guzman, Bre-X's chief geologist, to meet with them and explain the falsified ore samples.
It was D-Day right there. That was when Steve was going to make the first confrontation and say, hey guys, you know, what gives here? We don't think you're on the level. And he never turned up for the meeting and never turned up after that anywhere.
We had a message from Jakarta coming in where they had heard that de Guzman had disappeared out of a helicopter, and he was the only person in the back seat of the helicopter and supposedly opened the door and jumped out.
Indonesian authorities claim to have found de Guzman's body and ruled his death a suicide. But some believe the case is not closed.
You know, the whole thing about his remains and how they were identified, it's all very questionable. I kind of feel like he's probably hanging out in the Philippines somewhere, enjoying his money.
Despite the Bre-X hoax, Freeport continues looking for another Grasberg, a geological holy grail hidden in the mountains of Irian Jaya. Like true grail seekers, those who have braved the quest have been transformed.
The country itself is so spectacularly beautiful that well, I always said it was a religious experience to go to work in the morning because the sun was just hitting the tops of the peaks, and it was just a wonderful place.
Some of the things that I'm going to remember for the rest of my life and things that I have a hard time talking to other people about are things like being in a helicopter at 18,000 feet at 6 o'clock in the morning and watching the sun rise over that mountain. It's magic. It's unbelievable.
When we were finally leaving for the last time, Ellie and I were in the helicopter, and you could hear this whoop, woof, 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 and a whole mob of natives came running down, trotting down, all dressed up in their finery. They're saying, well, you'll be back, boss, huh? You'll be back. And I thought we couldn't look at each other. We were both choked up on the way down, you know, knowing that was one of the best parts of your life is finished then.
I think the men who built this mine, I think, are really an unusual bunch from the standpoint that not only were they hard workers, you can find hard workers almost anywhere in the world. I think it was a vision that they had, which I think was inspired by the kind of terrain they were working in. No place has a physical toughness and splendor that Irian has. It was really a challenge. Man against nature, but nature at her most unforgiving, nature at her toughest. I don't think you can find any place on Earth where nature is any tougher than this.
Grasberg and Erzberg will forever remain monuments to those who discovered them, built them, and made them work. A tribute to the human courage and determination that, against stupendous odds, erected a superstructure above the clouds at the ends of the earth. Off the coast of Japan, there is a superstructure so immense it can be seen from space. The world's first airport in the midst of the sea. The largest man-made island of its day. The longest bridge of its kind. And one of the world's architectural masterpieces. But its brilliant design could not conquer a hostile Earth. Today, low-tech ingenuity saves its high-tech engineering. Is Kansai the airport of the future, or is it doomed to sink beneath the waves? Japan, where modern skyscrapers dwarf the monuments of ages past. Where timeless serenity mingles with industrial might. And one of the world's engineering marvels rises from the sea. A superstructure for the 21st century, the mile-long terminal at Kansai International Airport hovers like a giant silver bird atop a man-made island in Osaka Bay. Graceful in design, Japan's aerodynamic airport is a triumph of construction and a technological wonder.
It was quite extraordinary to me that when the building first opened, it was getting 10,000 visitors a day who were not there to fly, they were there to look at the building. And that says something.
To build the world's first ocean airport, architects and engineers probe deep into the laws of nature, searching for answers to the awesome challenges before them. Thousands of workers labored 7 years building the biggest man-made island of its day, more than 3 miles from shore in water 60 feet deep. Then crowning it with the world's longest building, the biggest public works project of the 20th century.
The airport is the first place and last place people normally see at your city. So you want it to represent something about your city. You want it to look good. You want them to have a favorable impression when they arrive. and when they leave. We don't build big cathedrals anymore, but we build big airports.
Today, Kansai International is a glittering masterpiece, widely regarded as one of the world's most beautiful airports and one of modern history's most daring engineering projects. Before Kansai, no one had ever built an island in water so deep or so far from land. From steel girders to workers' lunches, everything had to be transported to the construction site by boat. To create the island, work crews had to move 750 million cubic feet of earth, pound 1 million steel columns into the ocean floor, and labor over 10 million man-hours.
I scouted the location by helicopter, and I thought, oh my God, this might be a big challenge.
Why did Japan take on the challenge of building an airport on the sea? Because daunting as that challenge was, building Kansai International Airport on land would have been next to impossible. Kansai is a 10,000 square mile region in central Japan, straddling the island of Honshu, some 300 miles southwest of Tokyo. Within its boundaries lie two of Japan's most important cities, the sprawling industrial centers of Osaka and Kobe. In the 1960s, Kansai cities were losing ground. Japan's imports and exports flowed through Tokyo. To compete with Tokyo, Kansai needed a new international airport.
This airport was not only very important for Kansai, but also for the whole Japanese economy. Before Kansai Airport, manufacturing companies based in Kansai had to send their cargo all the way to Tokyo to ship it out of the country. That was very inconvenient.
Osaka's airport, Itami, sat in the middle of a residential neighborhood, dangerously hemmed in by buildings. The constant roar of jet engines disturbed its neighbors.
There's no way that you can get around it. The airplanes fly over, they make noise, they have particles of emission from the jet engines, and those end up in people's yards, on people's roofs, and in people's ears when they're trying to watch television or have a barbecue. Too many families lived in that area, so the potential there was a dangerous one if something ever went wrong. Thank goodness it didn't.
At the far end of the runway, just on the approach, there was a school. We were always cognizant of the school being there, and which is not the greatest thing.
Expanding Itami was out of the question, but so was finding land for a new airport. In heavily populated Japan, there was little empty land and few people willing to give up land they owned. In 1969, Tokyo began construction of an international airport at Narita, a distant suburb largely populated by farmers. When the government confiscated farmland to build the airport, protests exploded. Outraged farmers besieged the Narita construction site. Leftist radicals fired rockets across the runway. Police arrested more than 3,000 activists. 7 people died. Protests delayed construction of Narita Airport for nearly a decade.
In the Narita case, the government carried the plan forward without giving much information to the people. You might say the government forced its plan on the people, and that caused a strong movement against the construction.
The best way to deal with noise pollution and angry neighbors was to avoid them altogether. Kansai decided to build its new airport on the waters of Osaka Bay.
There's nobody out there to sue them in the middle of Osaka Bay. Maybe a marlin here or there or something like that.
With no neighbors to disturb, a water airport could stay open 24 hours a day, making it even more competitive with Tokyo. But the plan had other perils. Osaka's fishermen might oppose a water airport as bitterly as Narita's farmers had battled an airport on land.
Fish travel their own routes, which the fishermen know. If there's any change in those routes, it's very difficult for the fishermen to catch fish. It's not like the fish travel along marked highways. To find them again is very difficult.
To avoid another Narita, authorities offered the fishermen a huge fee as compensation for disturbing their fishing grounds. The fishermen accepted. Politically, the path was now clear. But the project's troubles were only beginning. By locating their airport on water, Kansai's planners had avoided battles with outraged citizens over land. Yet they would soon find themselves battling a far more powerful force, the force of nature itself. Japan's 4 main islands have been called the most geologically treacherous real estate on Earth. 9 major earthquakes greater than magnitude 7 struck in the 20th century alone, killing over 150,000 people. Thousands of smaller temblors shake Japan every month. An earthquake's worst damage is often to structures built on landfill, which liquefies when shaken. When it isn't shaking, Japan is reeling from some of the deadliest storms on the planet. Since World War II, hundreds of typhoons have ravaged the Japanese coastline, killing nearly 7,000 people. A typhoon's cyclonic winds can whip up what meteorologists call a storm surge, a dangerous rise in sea level. On September 21, 1934, a storm surge raised the level of Osaka Bay 10 feet for several hours. That typhoon killed 3,000 people. 3 miles from shore, the new Kansai Airport would be fully exposed to a typhoon's fury. Would a typhoon someday tear the new multi-billion-dollar airport apart? Would its foundations dissolve in an earthquake? Would storms or earthquakes sever its links to land? The new Kansai Airport had to survive some of nature's most powerful onslaughts. Engineers designed an island 2.5 miles long and nearly 4,000 feet wide, framed by a huge rectangular seawall, whose perimeter would be 7 miles long. Into this massive frame, they would pour 750 million cubic feet of earth. It seemed like a simple plan, a larger version of other projects Japanese engineers had successfully completed many times before. In land-starved Kansai, the shore is lined with industries built on man-made land. But 3 miles from shore, conditions were very different.
The seabed is something like 100 meters or so depth of soft clay. So soft, in fact, that if you could drain the sea away, you wouldn't be able to walk on it as a marsh.
Tests showed that the airport island would rest on 2 levels of ocean-bottom clay. The upper layer, called alluvial clay, didn't worry engineers. They had built on it many times before. But 3 miles from shore, there was a deeper, older stratum called diluvial clay, extending 1,000 feet below the alluvial layer. Engineers had never built anything on this diluvial clay. No one was sure how it would react when the world's largest man-made island began pressing down on it.
So the new problem is how to predict the compression of deep-seated old stiff clay. That's, I think, the first case in the human engineering history.
In order to know the condition of the foundation ground, we developed a method of sampling the clay itself. We calculated things like strength and pressure density correlation to learn the characteristics of the ground.
Scientists analyzed core samples from the ocean floor and gave differing predictions of how far the airport might sink into the clay. Some believed it would sink only 19 feet. Others insisted it could sink as deep as 25 feet. Officials made a fateful decision. To save money, they rejected the predictions of deeper sinking and planned an airport that would sink only 19 feet. January 1987, with prayers for the safety of the workers, construction of Kansai International Airport begins. The first task is to strengthen the soft ocean floor clay so it can support the airport's immense weight. To strengthen the seabed, engineers use a well-tested method known as sand draining. Specially designed ships float over the construction site, first spreading a 5-foot layer of sand over the ocean floor, then hammering 1 million pipes deep into the clay. It's a fully automated process, controlled by shipboard computers. Next, enormous barges equipped with pile drivers force sand into each pipe. Finally, the computer-controlled ships pull out each pipe, leaving 1 million columns of sand. When the finished airport presses down on the waterlogged clay, its weight will squeeze the water from the clay into the sand piles, draining the clay to make it harder. But the sand drains cannot reach the deeper diluvial clay. Nothing can be done to stabilize it. With sand drains in place, work on the seawall begins. To keep waves from washing away its rubble slope, seawall workers must armor its surface with massive stones. 60 feet below the surface, divers guide these armor stones into position. The divers are veterans of many underwater construction projects, but none as deep and as far from shore as Kansai Airport. They face deadly hazards in the turbulent ocean depths.
At this place, we set stones that are about 1 to 2 tons each in the water. It was far from the shore, so there were bigger waves. It was a challenge for us. We did it even in tough situations like in bad weather. One guy had his leg amputated at the thigh because the waves moved a stone and it smashed into his leg. We were always close to death in a way.
Despite the dangers, work on the seawall continued as workers maneuvered 69 gigantic steel chambers into place. Each of these mammoth casings was 75 feet high, 75 feet in diameter, and weighed over 200 tons. Pile drivers pounded them into the ocean floor to form the corners of the seawall. Workers placed 48,000 four-pointed concrete blocks along the seawall's south and western edges, where the sea was strongest. These strange-looking blocks are designed to dissipate the force of breaking waves. By June 1989, 2.5 years after work began, the seawall was finished. Now, the airport builders had to find enough soil to fill it. On the mainland, crews worked round the clock excavating 3 entire mountains. Huge barges transported the excavated soil to the airport site. For 3 years, a fleet of 80 ships dumped earth inside the seawall until it rose over 100 feet above the ocean floor. Global positioning systems directed each barge through its onboard computers, telling it exactly where to dump each load. The island fill combined 3 different sizes of coarse rock and gravel. Engineers hoped this mixture would resist liquefaction in an earthquake. Slowly, the airport island emerged from the sea, despite violent protests. The same leftist radicals who assaulted Narita Airport launched a mortar attack on one of the quarries supplying the island's fill. No one is hurt, but the exploding mortar rounds ignite a forest fire, which rages for hours. It is only one of more than 24 attacks on the airport project during construction. Planting bombs, firing rockets, and setting fires, the radicals destroyed equipment and injured 4 people. But work never faltered. While some workers built the island, other crews were busy linking it to land. In the fall of 1987, giant floating cranes brought the first pre-assembled bridge pier to Osaka Bay, anchoring it on pilings driven into the seabed. By the spring of 1989, 29 of these piers stood in line between the airport island and the mainland. The gigantic cranes returned with enormous steel modules, each over 500 feet long and weighing over 4,000 tons. Bolted together, they formed a double-decked truss bridge over 2 miles long, 1/3 longer than the Golden Gate Bridge, with a price tag of over $1 billion. Its upper deck was a highway, its lower deck a railroad track. Flexible joints connected its spans, so the giant bridge would bend, not break, in a typhoon's deadly winds. By March 1990, the bridge was built, and the airport island was nearly complete.
This man-made island was created by the effort, sweat, blood, and tears of over 10,000 people who worked very hard.
But the island builders' celebration was a muted one. By then, they had discovered a new and relentless threat, an enemy so powerful it could defeat them. Spring 1990, Kansai Airport's man-made island is nearly finished. Construction firms prepare for the monumental task of building the passenger terminal. But in March, engineers make an alarming discovery, which threatens to destroy the project. Kansai Airport is sinking into the sea. Airport officials had expected the island to settle some 19 feet into the soft seabed. But by March 1990, it had sunk 27 feet and was still sinking over 2 inches every month. No one knew when or if the sinking would stop.
No one knows exactly what to do, because it's quite different from our past experience. It's big size and very heavy load. These 2 factors combined give rise to the effect of waking up the sleeping lion.
The revelation stunned Osaka and the nation. The international press dubbed Kansai Japan's sinking airport. Some compared it to history's most notorious engineering blunder, the Leaning Tower of Pisa. After 20 years of planning, 3 years of construction, and billions of dollars, it appeared that Kansai Airport might never be built. What had seemed genius now appeared to be merely hubris. As public outrage grew, the president of Kansai Airport resigned. Engineers scrambled to find a solution, if there was one.
We cannot stop the compression of this type of soil, because We can cope with the soil with various new techniques down to 50 or 60 meter depth. But now the soil in the question is 200 meter deep. So we cannot apply any sort of artificial technique to that.
To keep the airport above sea level, workers piled an extra 11.5 feet of soil atop the island at a cost of $150 million. They dropped a 20-ton weight 100 feet onto the runway to compact its soil. They decided to pave the runway with asphalt because asphalt would absorb earth movements better than concrete. Yet their greatest problem remained unsolved. It was time to construct Kansai International's passenger terminal. But how could they build it on a sinking island? While engineers debated, the terminal's architects perfected its design. Noriaki Okabe had spent 25 years in Europe working with world-renowned Italian architect Renzo Piano. Together, they had created some of the world's most remarkable buildings, including the famed Pompidou Center in Paris. But at Kansai, they faced the challenge of their careers. The Kansai terminal had to be small enough to fit on a man-made island, yet big enough to house all the complex functions of a modern international airport. High enough to inspire passengers with its beauty, yet low enough to allow air traffic controllers an unrestricted view of every airplane on the tarmac. It seemed an architectural paradox.
Architects usually get stimulated by looking at the site before the work starts. This project was unique because there was no site yet. There was no ground.
Seeking new sources of inspiration, the architects turned to the structures of nature. Nature's geometries solved their most difficult problem: how to make the terminal both high and low. Answer: the toroid, the remarkably versatile shape of magnetic fields, convection currents, bicycle tires, donuts, and fruits. In its architect's eyes, the enormous Kansai terminal is only the small visible portion of an immense toroid over 20 miles in diameter, circling through the Earth. The toroid shape allows the building's center to soar 85 feet high, while its wings taper to 20 feet, inspiring visitors, giving the control tower a clear view of aircraft, and making architectural history.
It is the most pervasive form in the natural world, the toroid. And so far as I know, this was the first time it had been used, certainly the first time it had been used in a big structure. Since Kansai was designed, the toroid has become a very fashionable form, particularly architects working with British engineers who've mastered how to use this form. But it was innovatory at its time.
The toroid solved the problem of designing the passenger terminal. But still unsolved was the biggest problem of all: how to construct one of the world's biggest buildings on an island sinking into the sea. By the spring of 1990, an international team of architects and engineers had created a cutting-edge design for Kansai Airport's passenger terminal. The blueprints were ready, but the terminal could not be built until the builders solved a puzzling problem. The completed terminal would weigh only half as much as the vast amount of earth excavated for its foundation from an island that was sinking into the sea. The lighter terminal would not sink as fast as the heavier island. As island and terminal pulled apart, the massive structure was certain to crack.
The problem is not that the building is sinking into the ground, but that the ground is sinking faster than the building. People don't realize, but the building actually floats in the earth. That's one of the reasons they have to have basements. They're like ships. And that's particularly true of new earth. So Kansai Airport has a ballast of 250,000 tons of very dense iron ore in it.
As they prepared to build the terminal, engineers lined its foundation with an 8-foot thick layer of crushed iron ore, hoping the extra weight would help the terminal sink as fast as the island. On April 24, 1991, terminal construction began. It would take nearly 3 years to complete. Following the architect's blueprints, workers erect some 30 steel trusses to support the roof. Each of these massive trusses weighs over 200 tons. Then, workers assembled the terminal's skeleton of 250 ribs, each forged in England and carried by ship to Japan. They installed nearly 5,000 panels of glass on its sweeping front, carefully encasing each panel in a rubber frame, so it will move, not break, if an earthquake or a typhoon sways the building. They cover the roof with 90,000 stainless steel tiles, tested to withstand fierce typhoon winds and violent seismic shaking. With painstaking effort, workers lay each of these tiles individually by hand. High ocean winds make their task even more difficult and sometimes impossible. By 1993, the terminal's enormous shape rose above the airport island. Over 1 million architects, engineers, and workers around the world had contributed to its construction. Today, Noriaki Okabe wanders with pride through a superstructure. Widely proclaimed as one of the most brilliantly designed airport terminals in the world.
It's a very big building, Kansai. It's possibly the longest building in history that is not a factory, but one huge room occupied by people. But what's very striking is the very intimate relationship it sets up between you, the person moving through, and the building that is making way for you, leading you through, guiding you through. This is a very extraordinary sense to get in what's a highly technological, enormous building. I think that's one of its most extraordinary achievements.
Arriving by car, rail, or hydrofoil, passengers enter what the architects call the canyon, a vast open space 100 feet high and nearly 1,000 feet long. 4 cavernous stories linked by humming escalators and whirring elevators. Designed to impress, but also to inform.
The reason why this space is so huge is so that people can see where they are going. Any spaces in this structure can be seen from wherever you are.
As they move beyond the canyon, passengers don't have to navigate a sprawling multi-terminal complex as in many other airports. Domestic and international arrivals and departures are vertically stacked on the 4 floors of the terminal building. Passengers travel up and down a central set of escalators, which carries them to arriving and departing domestic and international flights. Finally, they emerge into the terminal's spectacular departures area, a kind of aviation cathedral stretching over 1 mile long, making Kansai Terminal the longest building in the world. Automated trains whisk passengers to its 41 aircraft gates. Travel time from the central terminal to the end of each wing is only 90 seconds. An ingenious system solves a baffling problem. How do you air condition the world's longest building?
If you blow a big air jet into a very large space, it travels so far. Now, what we did on Kansai, which I think is quite innovative, was to create a shape of ceiling which was similar to an air jet shape, and to stick the jet to the ceiling. If you make a jet of air stick to the ceiling, then it travels up to twice as far as it would if it was in free space, and it will cause a much bigger circulation current.
Gigantic yet graceful, 18 nozzles send air flowing along the ceiling into sheets of smooth fabric, which keep it circulating. Colorful mobiles reveal the moving air.
It's the first time it had been done at such a big scale, and it's the first time in which the shape of the roof and structure was exactly shaped to the decelerating air jet. It's a building that is most in step with what is happening in the sciences and must herald the future.
But when it was finished, Kansai Terminal's future remained in doubt as the island beneath it continued to sink. Even with its iron ore ballast, the terminal would almost certainly crack as the heavier island beneath it sank. Engineers devised a surprisingly simple solution. In the basement, 900 concrete columns support the building's massive weight, but that's not all they do. As the terminal sinks, sensors on the columns alert computers in the central control room. Technicians scan the computer screens, looking for trouble spots.
This screen shows the current subsidence of the terminal building. The areas in red have less subsidence, and those in blue have more.
When the computers warn that the sinking island threatens to crack the terminal, workers raise or lower the columns in the endangered area to keep it level with the ground. They use powerful hydraulic jacks, which can move columns up to 15 inches if necessary. Workers slide iron plates under the jacked-up pillars to hold them up after the jacks have been removed. It's no different than sliding a matchbook under the leg of a wobbly coffee table. But Kansai Terminal has 900 legs and weighs nearly 3 million tons.
It's a solution which, as I understand it, has been used before in Japan, and it might seem a bit primitive, but I have no reason to suspect that it's anything but perfect for the problem.
In fact, everything in the Kansai Terminal's basement is designed to move up and down. Air conditioning and other systems are bolted to the ceiling instead of the floor. Doorways feature several inches of extra room overhead. In their zeal to save the Kansai Terminal, engineers tried to think of everything.
This terminal building is being adjusted at all times. I'm on the stairs which connect the first floor and the basement. The step where I'm standing right now was the height of the floor when the airport opened. In the last 4 years, we jacked it up 3 times, and as a result, we added 2 more steps here.
Measures like these helped the airport cope with its sinking island, but they also delayed its completion by over a year. On September 4th, 1994, Kansai International Airport finally opened for business. The Emperor's son, Crown Prince Naruhito, and his wife, Princess Masako, attended the opening ceremonies. 11,000 police stood guard in case radicals attacked. As they celebrated, the airport's proud builders could not know that nature's fury would soon assault their masterpiece. Dawn, January 17th, 1995. Kansai International Airport has been open 15 months. As this day begins, it will be severely tested. At 5:46 a.m. on January 17th, a devastating 7.2 earthquake rocks the Kansai region. The massive temblor is the deadliest quake to strike Japan since the Great Tokyo earthquake of 1923.
I was still in bed because it was quite early in the morning. It was a very huge, up-thrusting movement. Dishes jumped out of the cupboard in my house. I had never experienced an earthquake that big before.
Hardest hit is the city of Kobe. The city's wharf rises 10 feet. Cranes topple, and a harbor breakwater sinks. Rail lines and major highways buckle. The quake kills more than 5,000 people and injures over 25,000. More than 300,000 people lose their homes. Kansai International Airport is only 18 miles from the epicenter.
When the earthquake hit, the first thing I thought about was my family. Then I thought about the Kansai Airport. Maybe the glass has broken.
Fearing the worst, officials rush to the airport. Outside the terminal, they find a cracked sidewalk and few other signs of damage.
I raced to the airport in my car and arrived before 7 o'clock. When I rushed into this control room, all the machines were operating properly.
The airport had survived one of nature's deadliest assaults, or had it. With so much devastation nearby, it seemed too good to be true.
When I came to Kansai Airport, we could see Kobe was burning. Although you couldn't see anything wrong, I had great anxiety about the airport's invisible parts.
The inspections confirmed that the airport's anti-earthquake measures had worked. Engineers had used a mixture of large rocks to build the airport island. When the earthquake hit, this coarser landfill absorbed the shaking. Had the fill rocks been smaller, the island soil might have liquefied. Airport buildings would have collapsed, as so many other structures did. Instead, the delicate-looking passenger terminal proved as tough as its architects had hoped, thanks to its ingenious design.
For example, at this bridge, that side of the building is fixed, and this side has a sliding system to absorb the shock. At the time of the Kobe earthquake, this point moved almost 4 inches.
Even the terminal's massive glass walls were intact.
It was important not to transmit the movement of the roof in an earthquake to the glass wall below. We designed a system which absorbed all movements between the two structures by using sliding or rotating joints. During the Kobe earthquake, this system worked so well that not a single pane of glass was broken.
Kansai International remained open throughout the crisis, serving as a staging area for arriving rescue teams and supplies.
The building was, in fact, the building closest to the epicenter of the earthquake that destroyed Kobe. That doesn't mean to say it was hardest hit, because the buildings in Kobe were equally hit hard. But because it'd been designed to cope with all these things, it rode it out without any damage at all.
Surviving the Kobe quake was a triumph for Kansai's beleaguered engineers. The airport had passed a significant test of its engineering and design. 3 years later, it would face another, as nature struck again. September 22nd, 1998. A powerful typhoon slams into the Japanese coast, killing 10 people and injuring more than 200. Winds clocked at 130 miles per hour roar across Osaka Bay, whipping up dangerous waves and slashing rains. By noon, the storm's full fury reaches Kansai Airport.
The typhoon had increased speed to the point of where we were arriving at the same time, and we did have quite strong winds. But the difficult part was the people who tried to park us on the ground to keep them from getting blown away, literally. Right after we landed, in fact, the airport authority closed the airport because of the difficulty on the causeway between the mainland and the island. It became unusable for vehicular traffic. When we were crossing the causeway going to the mainland, there was a motorcycle who went down, and there was a couple of accidents that we had seen, so it was smart of them to discontinue.
By evening, the typhoon had passed, and Kansai Airport resumed normal operations. The terminal's roof had suffered minor damage, but airport officials felt lucky. The typhoon might have threatened the sinking island, now standing only 17 feet above sea level. Kansai's ingenious jacking system keeps the terminal building level, but it cannot stop the island from sinking. Every year, the airport sinks a foot deeper into the sea. Scientists debate how much farther the island will sink, but some believe that if it keeps sinking, a typhoon's waves will someday swamp the airport.
Next countermeasure is how to prevent the invasion of water. We are going to start with this sort of countermeasure maybe 5 or 10 years time from now. If the top elevation of the man-made island going down beyond some special value, in high tide time or typhoon time, it's quite easy to seawater to flush inside the island. That's our greatest concern at the moment. Airplane cannot land in the pond, so runway must be dry all the time.
To keep out storms, engineers must build a higher seawall around the airport. But this is not the only challenge they must meet. If Kansai Airport is to survive economically, it must expand. Since it opened in 1994, its volume of international flights has nearly doubled. Its single runway can handle 160,000 takeoffs and landings a year. By the year 2007, it will reach that number. Without a second runway, Kansai will choke on its own traffic. The airport plans to build a second runway and terminal on a parallel island connected to the original airport. But this island must be built in water even deeper than the first. The seabed is even softer. Scientists believe the second island could sink even farther than the first.
At the new site, we have to construct the island on a bad, soft foundation. Since it is impossible to do away with subsidence, we are thinking of constructing a second terminal building between the old and the new islands, which will float on the sea like a ship. Then we won't have to worry about it settling at all.
But sinking isn't the only obstacle to expanding Kansai International. Battling the sinking problem drove the airport's price tag to $15 billion, 40% over budget. Interest alone on the airport's debt is $560 million a year. Building a second runway will cost an estimated $14 billion more. Even if it never slides beneath the waves, Kansai International may sink beneath the crushing burden of its debt. And yet the second runway must be built. The airport's future, and perhaps the lives of its passengers, depend on it.
If you're going to be a major hub airport, you're going to really have to have 2 runways. Because what happens if something goes wrong? What happens if you have an airplane that blows a tire and you're really a hub? A hub brings in a lot of airplanes at one time.
When you're considering the number of tires on each 747, you blow one tire, as far as the airplane is concerned, you'd never even know it until you cleared the runway. However, the carcass is on the runway, and you certainly wouldn't want an aircraft following you to encounter that. It could be a major disaster, both landing gear and or engine-wise. So they'd have to sweep the runway, and that takes time. And when you have 10 airplanes or 12 airplanes waiting for arrival, it gets to be a very ticklish affair. So a second runway is very, very important.
Though surrounded by water, Kansai International Airport finds itself between a rock and a hard place. Hong Kong and Singapore now have new state-of-the-art airports. Tokyo's Narita is building a second runway. To hold its own in the highly competitive world of Asian aviation, Kansai must expand. Engineers need the second island as much as airport officials do. They want to build higher seawalls to keep typhoons from someday swamping the first island. To build those walls, they must temporarily close the original runway. Yet the immense cost of saving the airport, added to its already huge debt burden, may cripple its future. Kansai International Airport may never fulfill its builder's dream of becoming one of Asia's leading aviation hubs. But somehow, it's not Kansai's troubles most people remember. It's Kansai's achievement. Its landmark design has won the praise of critics the world over and earned the approval of the thousands of awestruck travelers who pass through it each year.
I think it'll be some time before what has been achieved there will be fully understood. The lessons will be learnt probably in the 21st century more than in the next few years from Kansai. People will understand more deeply what's been achieved there.
I believe that the legacy that people are going to remember about the airport is that they built something that was never heard of before for an airport, and that even though they had problems, they found very good solutions to make it work, and in fact became an engineering marvel in several aspects. Number one, that they were able to fill it, and then when it didn't settle at the rate that somebody had calculated, that they were able to solve that problem and continue to operate.
Whatever its future holds, Kansai International Airport will always be a monument to a bold vision. A vision that dared to accomplish something no one had ever tried before. A vision that literally moved mountains, created land in the midst of the sea, and graced Japan with one of the world's most beautiful airports.
Rising from beneath the waves, a silent predator suddenly strikes. For almost a century, submarines have patrolled the world's oceans. Their missions, even their construction, cloaked in secrecy. Now, we'll take you where cameras have never been allowed before, to witness the incredible birth of a modern nuclear submarine. About to embark on a potentially dangerous mission, this is the story of the most complex military machine of the 20th century, a superstructure called Seawolf. It's a ritual like no other. A centuries-old tradition of pomp and pageantry welcoming a new ship to the fleet. But while the christening of this vessel follows a time-honored custom, that's where tradition ends. This is a ship for the next century. An entirely new class of submarine meeting the water for the first time.
Bearing 188, ATF SB11. 400 feet, coming 800 feet.
A showpiece of revolutionary design and construction techniques. The nuclear-powered USS Seawolf takes its place in the ocean as the most advanced and lethal submarine ever created.
Stay on the record 080.
It's taken over 3,000 workers more than a decade to build what the Navy calls the most complicated machine on Earth. The crew of Seawolf has endured years of training to earn a place aboard this mechanical marvel. She is a prototype for the Navy's undersea future. But before they can claim the title of sovereign of the ocean, man and machine must pass a complex and dangerous series of tests known as the sea trials.
And battle station. Sierra 3-2, a submerged contact. My intentions are to engage this contact and stay course 120.
The stakes could not be higher. In the post-Cold War era of budget cutbacks, the Navy is relying on Seawolf to prove it can do more with less.
Contact Sierra 3-2.
If this ship fails her sea trials, the entire future of the Navy submarine program will be affected.
Firing point procedures.
The 14 officers and 124 enlisted men of Seawolf are well aware that they and the submarine's builder are under intense scrutiny.
Shoot on generated bearing.
The number of Seawolves approved for construction has already been slashed from 30 to 3. Workers at the electric boat company who built Seawolf have seen their numbers drop from 25,000 to 7,000. To them, a successful sea trial could mean the difference between economic life and death.
Very well, steady course 050. 050 online. Chief of watch, stand down from battle station.
But as the world's most sophisticated weapon slowly descends beneath the waves, the ultimate test will come from the ocean itself. At bone-crushing pressures deep below the surface, there's no margin for error. There are few places in the world large enough and sophisticated enough to build a nuclear submarine. This is one of them, the Electric Boat Company's machine shop in Quonset Point, Rhode Island. For the first time ever, the company has allowed cameras inside to witness the birth of a nuclear submarine. Here, giant pipes are twisted into intricate shapes, while massive grinding machines polish tons of special metal alloys into parts that will become the body of Seawolf.
There's about 8 million parts on a submarine. Those parts have to fit together electronically, mechanically. The tolerances are extraordinarily close.
The Electric Boat Company was co-founded by submarine pioneer John Holland in 1899. While the construction of Seawolf marks a new chapter in the history of underwater vehicles, like all subs, its life began on the design table. From the 19th century through the Cold War, submarine construction has always required enormous amounts of precise planning.
For instance, on Trident, there were 10,000 drawings that defined that ship. And there were probably 5 or 6 revisions to the 10,000 drawings. So you had 60,000 pieces of paper.
It's been about 30 years we designed a new class of submarines. In those days, when you designed a submarine, you just used slide rules. There was a lot of hand calculations. And so when they designed Seawolf, it was computer-aided. It was the first time we did that.
When Seawolf was designed in the 1980s, the computer revolution was just beginning. With the advent of computer-assisted design, or CAD technology, her creators could drastically reduce the staggering amount of hand calculations required. Now, basic design measurements such as length and diameter could be visualized in ways the early pioneers couldn't imagine. But the design process was still full of challenges. The 3 main problems facing modern Navy designers today were also faced by their forefathers. First, how to create a vehicle that could stay underwater for extended periods of time. Then, how to install enough weaponry to make it a viable threat. Finally, how to remain undetected. In the past, submarines were constructed by welding together steel plates to form the hull. Then the machinery, or guts of the sub, would be lowered inside through openings in the top. This was the primary method of submarine construction from World War I through the Cold War. The Cold War was one of the most volatile and dangerous times in American history. As the arms race between the United States and the Soviet Union escalated, the government turned to its undersea force for defense. The Navy developed two kinds of submarine classes, the ballistic missile submarine and a smaller class of subs, the attack class. The ballistic subs, often called boomers because of their enormous firepower, were essentially large mobile platforms for launching nuclear weapons.
3, 2, 1.
Deployed on secret missions throughout the world's oceans, the ballistic missile submarines served as a threatening deterrent to an enemy first strike.
Weapons con, you have permission to fire. Note 1.
Their companion class, the attack subs, were smaller and faster than the boomers. These subs were designed to do exactly what their name implied: attack, quickly, silently, and with deadly force.
Shoot!
Following the Cold War, the threat of a superpower conflict decreased, while the likelihood of smaller, regional conflicts increased. In response, a new kind of submarine was needed, a submarine like Seawolf.
The Gulf War with Saddam Hussein actually started, the attack started with a couple of missiles out of a submarine, hundreds of miles away. It keeps your personnel safe and has the ability to be used in every conceivable situation.
For this new class of submarine, a new building approach was employed. The Navy created Seawolf using a modular construction method. For the first time, a submarine would be built as a series of modules, with the piping, machinery, and fittings installed at the same time. This hull cylinder, about 40 feet in diameter, is about to become part of a larger, complete module. Using this new method of construction, the hull will not only be much stronger, but maintenance on the sub will also be easier. In the past, engineers would have to cut holes in the pressure hull to add or remove machinery. This time-consuming, labor-intensive process required extensive recertification tests. Now, machinery can fit through special openings that are covered by a watertight hatch, increasing the efficiency of the construction process and the strength of the hull. Even a pencil-sized puncture in the ship's hull would bring in water with the velocity of a bullet fired from a rifle. To learn how to survive against such impossible odds, the crew must now face their own certification process. That training begins here at the Naval Submarine School in Groton, Connecticut. These trainee submariners know that someday they may face a situation of life and death, an emergency in which their response will either save the ship or send it to the bottom of the sea.
For the water and enter lower level bills. Enter lower level DC Central I.
During World War II, submarine crews in the Pacific faced impossible odds with terrifying regularity. Under constant attack from Japanese depth charges, submarines became the final resting place for thousands of American servicemen.
Coming on, fire one!
Despite the losses, American submarines inflicted major damage on the Japanese Navy and merchant fleet. One after the other, these steel sharks rolled out of shipyards as fast as they could be built. In response, the Japanese tried every possible method to turn back the U.S. subfleet, including propaganda.
We know very well that American submarines have headed west from Pearl Harbor. If American submariners are wise, you will turn back. Certain death awaits you over here.
But neither depth charges nor propaganda could silence these warriors of the deep.
Down periscope, set, fire!
And the American submarine fleet dramatically affected the war's outcome.
The submarine force represented just a mere 2% of a very, very large Navy. The submarine force, with that 2% of the Navy, sank just about 55% of all the Japanese shipping that was sunk in the entire Pacific War.
Ultimately, the end of World War II was brought on by a catastrophic new weapon, an apocalyptic device using an energy source of unimaginable power. After the war's end, one man began experimenting with a way to safely harness this awesome power under the sea. He envisioned a new kind of submarine, powered by an energy source that would give it incomparable speed and stealth. His vision would lead to the awesome creation called Seawolf. Somewhere off the Atlantic coast, the world's most advanced submarine has begun its most crucial test.
Make your depth 300 feet.
Offshore deck, ship is on order depth.
Called the Alpha Trial. This is the first of 3 sea trials which will determine whether USS Seawolf is ready to join the fleet.
Offshore deck, make your depth 750 feet, 25 down.
Make my depth 750 feet, 25-degree down angle, aye, sir.
As it cuts silently through the water, its nuclear reactor provides an almost limitless supply of energy. 4 pounds of enriched uranium will provide the same amount of energy as 10 million gallons of fuel oil used by early diesel-powered subs. The advent of nuclear power was the most important development in the history of submarine construction. And now, as the most sophisticated submarine ever built continues its top-secret mission, it does so because of the dream of one man, Navy Admiral Hyman Rickover.
A qualified submariner and engineer with a strong faith in both the practicality and necessity of atomic propulsion.
He was a visionary of this business before we had the word vision.
His convictions and determination soon made him a dedicated and efficient spokesman for a nuclear navy.
Admiral Rickover was the first person to realize that nuclear power could turn the submarine into the most feared weapon on the planet. With this new power source, Rickover reasoned he could counteract the submarine's Achilles heel, the need for frequent resurfacing, which made them vulnerable to attack.
With no precedent and no technology available for such an undertaking, he had to start from scratch.
Prior to nuclear propulsion, particularly during World War II, submarines were essentially surface ships that were capable of submerging once in a while. But with nuclear propulsion, now you had a ship that was truly submersible.
But translating nuclear fuel into a practical energy source presented Rickover with a paradox. On one hand, harnessing the power of the atom on a submarine would be extraordinarily complex. But once accomplished, using that power to propel the sub would be relatively simple, utilizing the same principle as a steamboat. The process begins with a nuclear reaction. As control rods carefully reveal uranium in a sealed container, extraordinary heat is produced. Liquid is then pumped through the system. It carries that heat away from the reactor core and circulates cooler temperatures back to the nuclear fuel. The liquid then flows through a heat exchanger, where the high temperatures are transferred to water coursing through thick pipes. This assures there can be no release of radioactive materials during the energy exchange process. This tremendous heat turns water into saturated steam. The steam powers a turbine, which drives a generator supplying all the electrical energy needed to operate the ship. Excess power is diverted to energy reserves, stored in massive banks of batteries on board. Admiral Rickover understood that nuclear engines could not only generate more power, they could give submarines virtually unlimited range.
Underway on nuclear power. That was the terse message that sent the Nautilus and her crew into service.
In 1955, Rickover's theory was put to the test as USS Nautilus became the world's first nuclear-powered submarine.
Although the Nautilus' speed is a secret, it is known to be by far the fastest submarine in the world.
3 years later, Nautilus proved the submarine was now master of all the oceans, even those that were largely unexplored. In her historic 4-day journey, Nautilus opened a new frontier when it crossed from the Pacific to the Atlantic under the ice of the Arctic Ocean.
Flight for the men in the submarine service.
Passing directly under the ice packs of the North Pole, Nautilus completed the first undersea transit of this hostile environment.
A tumultuous harbor greeting is given the record breaker.
The ship returned to a hero's welcome.
A tribute to exploits that mark a new age in man's progress. A great step forward in the mastering of the 7 seas. Well done. Very well done.
Later in that same month, the crew of a different atomic submarine would establish a new endurance record for underwater operation. For 60 days, between August 7th and October 6th, 1958, the crew of this ship remained submerged beneath the forbidding ice floes of the North Pole. The name of that ship was USS Seawolf, predecessor to today's nuclear-powered wonder.
Here we go. 300 feet coming 800 feet. 700 feet coming 800 feet. Take charge your place, make it up to 800 feet.
On board today's Seawolf, submerging for 60 days is simply routine. With its nuclear-powered engines and ability to manufacture oxygen and water, Seawolf could theoretically remain underwater for years at a time. But beyond her extended range, nuclear power has also given Seawolf another important edge: speed. While her top speed is a closely guarded Navy secret, officials admit she cruises faster than 25 knots, about 30 miles per hour. Experts privately acknowledge Seawolf can actually travel much faster.
Well, it's funny. People try to figure out how fast a ship goes, and they always ask the crew. And the crew will say, they have an acronym, and they say it goes so fantastically fast that stuff falls off. You know, that's their little joke. But they won't tell you for sure how fast it goes. It is certainly a sports car compared to the other ones.
Helm left 10 degrees rudder, stay course 080.
In fact, even the designers of this undersea sports car were surprised by how fast she really is.
The ship is tremendously faster than what they expect, and people don't believe it. You go back to some of the scientists who did the original calculations, they refuse to believe it.
For all its high-tech power, Seawolf is still a warship. And life aboard this ship is no pleasure cruise. Every square inch of Seawolf is designed for maximum efficiency, which doesn't leave much room for human comforts. The crew eats in shifts. Over 130 men will pass through this compact galley 3 times each day. Space and privacy aboard Seawolf are luxuries the crew learn to live without. Even their sleeping quarters are designed for efficiency.
The reason why you call it hot racking or hot bunking is you have 3 guys to 2 racks. The reason why you have that is because you don't have enough space available for each member of the crew. The reason why they call it hot racking is because while you always have 1 on watch, you have 2 in the rack, and when that person gets off watch, that rack is still warm from the other person. So that's pretty much why they call it. And plus you jump around from rack to rack. You'll never sleep in the same rack twice.
It's not uncommon for some sailors to actually sleep in the torpedo cradles, luxurious accommodations for taller men frustrated by confined bunks. Because space aboard a submarine is at a premium, maximizing every available inch has always started with the design phase. During the 1980s, Seawolf designers were able to use emerging technologies to increase available space. For example, CD-ROM technology meant thousands of technical manuals and drawings required on early subs could be replaced by compact discs. No minor achievement, this freed up 350 cubic feet of space and eliminated over 6 tons of paper on board. A major tactical advantage of Seawolf is her arsenal of computers. This massive network of incredibly powerful machines are the most ever used on any naval vessel. Her communication software alone uses 6 million lines of programming code.
Seawolf submarine is probably the most complex product built by man in the world today. If you took the floppy disks, 1.4 megabit floppy disks, and took the data that's in this submarine and stored them in those floppy disks, they would be taller than the World Trade Center. There's just an enormous complexity of material, science, machines, computers.
Detection bearing 073, classified biologics.
The computer-driven sensor systems on Seawolf are so advanced, they can even pick up the most minute, natural sounds of the deep. What you're hearing is shrimp feeding in the cold waters of the Atlantic. The crew listens as dolphins swarm in for lunch. But beyond just hearing faint natural sounds, Seawolf sensors can detect and identify even the most silent of ships by their sound signatures.
Today's acoustic sensors, both on the submarine and also towed behind the submarine, have allowed us to be able to detect very quiet submarines and surface ships out to thousands and thousands of yards in range, out to many, many nautical miles. Those sensors combined with very improved and highly capable heavyweight torpedoes give us the capability to attack both submarines and surface ships almost at will.
Crew members say the difference between Seawolf and non-nuclear submarines is like comparing a biplane to a jet. But for all its space-age capabilities, the job of traveling beneath the sea remains extremely dangerous. And no mission is more dangerous than the Alpha Trial, the submarine's first meeting with the sea. As the crew of USS Seawolf continues their shakedown voyage, a mission from decades earlier casts an ominous shadow. A mission in which another nuclear submarine was being tested. A mission that would be cut short by tragedy. A tragedy that would shock a nation and forever change the nature of submarine construction.
The Navy's newest nuclear submarine, the Thresher, is launched at Portsmouth Naval Shipyard.
When USS Thresher was launched in July 1960, she was the first of her kind, a new class of submarine. Like the crew of Seawolf, Thresher faced a regular series of tests designed to further submarine exploration. But on April 10, 1963, the incredible danger associated with any undersea journey became all too clear. At 7:47 p.m., about 200 miles east of Boston, Thresher began a deep descent known as a test dive. For reasons still unknown, at 9:13 p.m., the ship radioed a message that it was experiencing minor difficulties and was attempting to blow its ballast tanks, a procedure used to surface during an emergency. 4 minutes later, a garbled message was received. Then, the horrifying sound of the ship breaking up. USS Thresher, along with her crew of 129 men, was gone.
It was a chilling and memorable day. It was almost like where you were when the president was assassinated, which I guess was also that year.
As ships and deep diving equipment scoured the ocean for the wreckage, investigators began a decades-long quest to find out why she sank.
In a remarkable series of pictures, the Navy photographs the ill-starred sub. In one photo, her number shows clearly. The tail section with the stern planes is plainly visible here.
Navy submersibles found what was left of Thresher in June of 1963 at a depth of over 8,000 feet. A Navy court of inquiry, however, was never able to fully determine the exact cause of her demise. No Navy official was more devastated by the loss of Thresher than the father of nuclear submarines, Admiral Rickover. While some critics attacked the performance of the ship's nuclear reactor, Rickover believed that submarine construction itself must change. He lobbied for improved fabrication techniques, better inspection methods, and more attention to emerging technologies and new ways of thinking.
When we lost the Thresher, we went from what had been a proactive approach to building submarines to a very strong reactive approach, and it focused our engineering discipline into what do we have to do to make a submarine safe for the people in the harsh environment, not just in wartime, but in peacetime too.
And so Thresher is not only historical memory, we remind people of Thresher as part of our submarine education and training. We go around and remind them the consequences of not adhering rigorously to the technical specifications and the processes. So it's still the backdrop for the SubSafe program. You know, here it is 34 years later.
The design and construction of submarines are highly specialized crafts, constantly being revised to accommodate new technologies. As technologies develop, the workers who build subs must also adapt, continually undergoing rigid certification tests which measure their skill and expertise. Even the body of Seawolf is made from a new material. The hulls of early subs were made from a high-strength steel called HY80. This material could withstand pressure of 80,000 pounds per square inch. The Seawolf class submarines are created using a new supersteel called HY100, able to withstand 100,000 pounds of pressure per square inch. This means that designers can now create submarines which can dive deeper than their predecessors of the same weight, although just how deep is classified. Or they can create new lighter weight subs, capable of reaching the same depths as the earlier heavier subs. But regardless of its weight, a submarine's effectiveness has always been judged by its ability to remain undetected. Once at sea, an engine hum, a mechanical noise, even a crew member's conversation could reveal the ship's location, with deadly consequences.
Stealth is the most important thing. A submarine maintains its capability and its safety by never being detected. For example, if there's a conflict, a hot conflict somewhere in the world, submarines, especially U.S. submarines, usually the first war-fighting or peacekeeping platform on the scene, and it does that without being detected. It can then provide information with surveillance, feed that information back to the president, and sort of the decisions can be made. And the submarine has the capability of doing that quietly, quickly, and it's virtually undetectable.
Two things you know. They know we have them and we can be there fast. And two, even when they don't know we're there, they're not sure we're not there because these things are stealth. So they could be thinking that, well, maybe around the corner there's an American sub, or maybe it's just off a little bit. And that will prevent countries, I think, from doing foolish things. And after all, that's much preferable to actually going to war.
To maintain stealth, every joint and substructure within the ship is designed to minimize sound and vibration. Even operating at top speed, Seawolf will be quieter than the older submarines were when idling at the pier.
It's quieter than any other submarine in the world, and that required an enormous amount of technology in quieting things like switches and valves and hydraulic piping.
The ship's inner decks are not attached directly to the hull, but rest on rubber mountings to reduce vibrations. Other sophisticated anti-detection strategies are also integrated into the construction process. Propellers are designed to produce minimal noise. Anti-detection tiles made from sound-absorbing plastic compounds line the inside of the hull. And finally, an additional layer of sound-absorbing material is applied to the hull's exterior when finished. While the ship is cloaked by a silent defense, its stealth-like capabilities also create a formidable offensive weapon. Whether gathering covert electronic intelligence, monitoring an enemy's shipping lanes, or detecting and deploying mines, Seawolf will be able to get in and out of dangerous waters faster than any warship ever created. But sometimes, the most deadly threat to a submarine crew comes from inside the ship.
Fire in the engine room, fire in the bilge.
I think probably the fire is the worst thing to have happen to you, because that's something very quickly, if you don't do the right thing, can get out of control. As you see, this is an enclosed environment. This is all we have.
Fire's out! Refresh hatch is set, eh?
If you get a big fire going, it gets very hot here in a hurry and very, very hazardous, and there's nowhere else to go.
Trapped hundreds of feet below the ocean's surface, a fire could wipe out a crew in an instant, or slowly consume the ship's life-giving oxygen supplies. It is a terrifying scenario, but one that is planned for in the design of a ship, in its construction, and at the Naval Submarine School.
Fire's out, refresh hatch is set.
This training doesn't end once on board.
Class Bravo, fire in the galley, fire in the deep mat, fire.
There's heavy smoke in the galley. I'm paying for calling the man in charge.
On a submarine, crew members constantly rehearse and plan for every conceivable situation.
There's heavy black smoke in the galley. We are currently searching for hot spots with the Navy. There are no hot spots. The fire is out. The ship is at periscope now. Preparation for emergency ventilating. All hands in the fore compartment ready EVs.
When building a military craft like Seawolf, designers must also plan for every eventuality. The most obvious and most dangerous is combat. Like an aircraft carrier, a submarine is divided into separate watertight sections. This way, if a torpedo should penetrate the hull, or if a fire should start in one section, the rest of the ship is still able to function.
Make your depth 750 feet, 25 down.
750 feet, 25-degree down angle. I sir, full dive on the stern planes. 25-degree down angle.
If the crew of USS Seawolf can pass its sea trials, it will be judged ready for combat.
Close about 2,000 yards. In about 4 minutes, we'll be at the firing point.
Tomahawk shape going to pivot tray A level. Starboard side, clear.
Carrying an arsenal of lethal weapons that can be targeted with pinpoint accuracy, the ship will patrol the seas with more military power than many countries possess.
Weapons coordinator, Captain, reports status of tube A.
Vector torpedo, normal launch, tube A.
A silent and deadly predator, Seawolf will be the most advanced, heavily armed attack submarine the world has ever seen.
All stations, arrival path is direct path. Carry on.
As the pieces of a new nuclear submarine are forged at this historic shipyard, workers at the Electric Boat Company now face an imposing task: transporting the giant sections to their dry dock facilities in Groton, Connecticut. To do this, modules weighing over 700 tons each are placed on the largest transport truck in the world. There are only 2 such vehicles in existence, and both were specially made to assist in submarine construction. When these 2 vehicles are used together, workers can move modules weighing over 1,400 tons. Now, they will travel by barge for the 60-mile journey from this Rhode Island machine shop to the Connecticut dry dock facility. As the pre-assembled pieces arrive at the dry dock, they are suspended in order and then pieced together to form the complete ship. Many months of assembly have been condensed into seconds to see this amazing process in action. As the pieces of this $2 billion puzzle are carefully assembled, even top-ranking Navy officials are amazed by the complexity of the operation.
The design, development, and construction of a submarine, I view it very much like eating an elephant. How do you eat an elephant? It's one bite at a time.
If the assembly of this submarine happens one bite at a time, then these are its sharpest teeth, the weapons systems. Now, with its body almost complete, the deadly arsenal is installed. On board Seawolf, 4 levels of robotically controlled storage racks can deploy a lethal force on a moment's notice.
Manned battle station.
Its Tomahawk cruise missiles can be placed with pinpoint accuracy, guided by a global positioning satellite.
I guess we could talk about San Diego to San Francisco. That's about 520 miles. I would say that if this missile took off from Jack Murphy Stadium, you could put it right about between Pitcher's Mound and second base down there in Candlestick Park.
Seawolf's anti-submarine missiles make her a fearsome underwater force as well.
She has stealth, she has improved sensors, and she has maneuverability. Everything that makes a fighter aircraft superior is what Seawolf brings to that underwater dogfight.
Seawolf is the most sophisticated military craft ever created. But the road leading up to this 20th century superstructure actually began hundreds of years ago. It was a road paved with danger. In 1775, only 25 miles from the site of the Electric Boat Company, a young Irishman named David Bushnell built this device called the Turtle. Driven by his intense hatred of the British and with the support of George Washington, Bushnell created an underwater craft that could place an explosive device on harbored British warships. Its name came from the design, resembling 2 turtle shells, 7 feet long and 4 feet wide. This craft of wood, iron, and leather could approach an enemy ship with a hand-cranked propeller and was able to stay submerged 20 feet below the surface for almost 30 minutes. Unfortunately, when Bushnell's device was tried on a British man-of-war, the attaching screw could not penetrate the copper sheathing on the hull. The Turtle was lucky to escape. But the theory of this unique weapon delivery system survived. The underwater sneak attack was born. During the Civil War, both sides developed submarines, but it was a Confederate version invented by Horace L. Hunley that became the first sub to record a torpedo hit on an enemy ship. It was a milestone that came with a terrible cost. The 60-foot H.L. Hunley used a crew of 8 to turn its propeller crankshaft, towing a single torpedo behind it. In 1864, in the Charleston, South Carolina harbor, the Hunley delivered its deadly cargo against the Union's USS Housatonic. The attack did little damage to the Union ship, but the exploding torpedo sank the Hunley. As primitive as these early craft appear, they actually use the same engineering principle as today's modern subs, the ability to submerge and surface by adding or subtracting ballast.
I went at 750 feet, used 25-degree down angle ISER.
During her sea trials, one of Seawolf's most critical challenges will be her ability to perform deep dives. Inside the hull are ballast tanks designed to temporarily fill with water. In the original sub designs, the ballast tanks were located port and starboard, as shown here. When the tanks fill with water, negative buoyancy is created, causing the vessel to sink. When compressed air flushes the water from the compartments, buoyancy returns and the ship rises.
700 feet, coming to 300 feet.
Seawolf also employs this basic principle of physics. But the ballast tanks on this ship are located fore and aft, so the ship can submerge or surface with incredible speed.
Officer deck, ship is on order depth 300 feet, sir.
The propulsion of early subs required exhaustive manual labor performed in suffocating spaces with no fresh air. These ships could only dive for brief periods, staying close to the surface in order to ventilate the craft. On board Seawolf, the same nuclear power that propels the ship also supplies the crew with life-giving oxygen. Water molecules are formed from 2 hydrogen atoms spinning around a single oxygen atom. On Seawolf, sophisticated machines use electromagnetic force to disengage the hydrogen atoms from the molecular structure, leaving pure oxygen for the ship's life support system. But it was another source of energy that first turned the submarine into a viable fighting machine. John Philip Holland was an industrious Irish immigrant who pioneered a double propulsion system for submarines. Holland's boat used a 50-horsepower gas engine for surface sailing, and then to keep the air breathable, a battery-operated motor while submerged. This dual-engine approach to underwater navigation gave the sub greater range and submergence capability, something that U.S. Navy officials realized in 1900. Able to dive to just over 100 feet, the Irishman's craft became the first submarine commissioned by the Navy. The crew of USS Holland became pioneers of a new world under the sea. Over the next 14 years, 25 more of these amazing devices called submarines were built. But beneath the waves, the United States would not be alone for long. May 1915, the ocean liner Lusitania is fired upon and sunk by a German U-boat. In under 20 minutes, over 1,100 passengers died, many of them Americans. The U.S. moves one step closer to war with Germany. During World War I, the potential of this new machine would be put to the ultimate test. The age-old ritual of enemies facing each other in head-to-head combat was replaced by the sneak attack.
Gyro 005 increasing. Shoot anytime. Fire!
The dream of John Holland and the early submariners forever changed the nature of warfare.
I think certainly that Holland, when he designed and built his first craft, probably never recognized where we would be today.
John Holland might never have imagined a vessel like Seawolf, but to the Navy, it marks the beginning of an entirely new class of submarine. High-tech subs that will begin in virtual reality and end up resembling science fiction. But first, Seawolf must prove to the Navy and the public that her design is sound, that her crew is ready. Now, as she nears the end of her crucial maiden voyage, the future of the next generation of subs hangs in the balance. Propulsion and life support systems have been tested. She has performed rapid dives to classified depths. Under stressful warfare scenarios, she has been deemed combat ready. As the end of USS Seawolf's maiden voyage draws near, Captain Dave McCall has witnessed what billions of dollars worth of machinery and a highly trained crew can really do. While young in age, McCall's crew are ready to become submariners.
It's $2.3 billion for this ship. And the first underway watch station an 18-year-old stands or occupies is he's driving this ship. He has his hands on the wheel of a $2.3 billion sports car. And that's a lot of responsibility. You have to want that kind of responsibility. You have to be ready to take it, and they choose themselves.
They have trained, rehearsed, and drilled. Now it's time to come home. But as Seawolf ends her maiden voyage, she is bringing back more than just the crew. Over 100 workers of the Electric Boat Company have gone with her on this dangerous but crucial first journey. While these shipbuilders were on board to perform tests and gauge the success of their handiwork, they also wanted to send a message. This was a ship that had been constructed properly, and they would put their lives on the line to prove it.
They've literally worked 24 hours a day, 7 days a week for 3 years with very little time off.
Years of hard work and grueling training have led to this one moment, the return of USS Seawolf to her base in Groton, Connecticut. To the trained observer, the presence of a simple wooden broom attached to the ship's superstructure tells them everything they need to know. The ship has performed a clean sweep of its first major test. The mission is a success.
probably our finest ship in the water today. It performs beyond expectations. After seeing it start from the early stages of design, early stage of construction where we just started bending steel, to watch the crew bring it alive, start operating it, we've been through a lot of major obstacles that would have normally brought another project to its knees and stopped it.
Against a backdrop of budget cuts and shifting political power structures, the designers, builders, and crew of USS Seawolf have achieved a stunning victory. Under a mandate to do more with less, they have rewritten the book on how to build a submarine. Now, the success of Seawolf will provide a blueprint for the submarine of the next century. A vehicle known simply as the new attack submarine. When production of these sleek new subs begins, they will be able to do everything Seawolf can, but cost less to build. That's because advancements in computer technology, just beginning when Seawolf was constructed, now provide designers with incredible new tools.
Tools today give us collectively as a community, the Navy, Electric Boat, our suppliers, the ability to go in fact integrate the very best design very early in the program.
This 3D generated sailor named ErgoMan is an example of this new space-age technology. Virtual reality programs like these enable designers to see what these subs will be like for human inhabitants before construction even begins.
We got to verify how low can we drop the sump.
Another significant change based on Seawolf's success is a brand new approach to the management of sub construction. In video teleconferences like this, the workers who will build the sub and the men who will travel in them interact with the designers and engineers at every phase of development.
Jimmy, if you just want to circle that, so our friends down in Washington can see that. That flange we're possibly talking about eliminating.
Today, we're not interested who comes up with a good idea. We make it a team effort to go produce the very best design for this country that we can produce. And that's exciting, and that's different than it's been in the past.
Seawolf and the new attack submarine are designed to evolve with technologies of the future. Soon, even the venerable periscope itself, a staple of submarines throughout history, may be replaced by powerful liquid plasma display screens. With the success of their first sea trial, the crew of Seawolf will continue a long and distinguished tradition. Even though this is a new ship with a young crew, they are traveling in the footsteps of those who have gone before, many of whom did not return. These are the names of United States submarines lost in the service of duty with all hands on board. Submariners say these ships and the men aboard them remain on eternal patrol.
We'll also be checking the tubes, shooting.
No one is more aware of the dangers of the deep than the men who will ultimately certify the vessel as being ready to join the fleet.
Good. Yes, sir. We'll head this way.
I am the person who signs for a submarine that it's ready to go to sea and it's sub-safe. And we do that through a very rigorous, disciplined process that literally takes thousands of hours of documentation, test, and retest.
Had Seawolf failed on its first mission, the consequences for the Navy would have been disastrous. Thousands of jobs, billions of dollars, and the lives of the crew were at stake. Now, for the thousands of men and women who created her, Seawolf's successful first voyage is a time of great emotion.
Well, you know, the day I give up the ship is going to be kind of like the day I give up my daughter to her husband at her wedding. It's going to be a hard day.
The design and construction of a nuclear submarine requires the imagination and determination of thousands. Forged from silicon and steel, they are born in giant factories. But here, beneath the waves, is where they will spend most of their lives. By the time Seawolf ends her final mission, it's difficult to imagine how far man will have ventured into the realm of the deep ocean. But waiting in the wings will be an entirely new class of undersea superstructures.
I hereby certify that he is qualified in submarines on board USS Seawolf.
And a new generation of submariners, piloting these guardians of the deep into the next century and beyond.
Congratulations, Past World Guard.
Thank you, sir.